All right, so we have looked at rotational motion in molecules and vibrational motion and translation. That's also a motion. We have asked questions about that on 3 exams. Hopefully by now you're like, okay, I got these 9 points, right? Total degrees of freedom, rotation, et cetera. But now we're getting into the electronic cloud. So we're looking at the motions of the electrons, which are not part of those total degrees of freedom. So the total degrees of freedom of 3n, that's just talking about the nuclei and what the nuclei can do and how they can move. So that's the whole molecule moving together in translation or rotating around an axis in rotation, or the nuclei moving against each other in vibration. But then now we have this whole flexible thing called the electron cloud, and it gets really complicated fast. If you just think about the periodic table, as you go up in element identity, you know, that number in the upper right corner is the number of protons, but that's also the number of electrons. So every time you add a carbon to a molecule, you get 6 more electrons. And so that gives you 3 degrees of freedom by adding an atom, but then it gives you, essentially, I don't want to confuse you, but it gives you 6 times 3 for the electrons. So it gives you 18 more things that can move, or 18 more movements, because the electron cloud can oscillate in the X, Y, and Z directions, okay? So the electronic cloud is really complicated, but that doesn't mean that this part's going to be any more difficult, because you already have been studying the electron cloud. You know about the S and the P and the D orbitals. That's what we're talking about, atomic orbitals, or the electron clouds around an atom. And now in this part of the course, we start looking at atomic spectroscopy. So what can that electron cloud do to absorb light or emit light? So we're no longer talking about vibrational excitation or rotational excitation. We're just talking about that electron cloud. And so we're going to see atomic spectra next. So we're looking at S to P transitions, P to D transitions, and so on. So this is just the electron cloud absorbing light and getting farther away from the nucleus if it absorbs light, or getting closer to the nucleus if it emits light. So that's what we're talking about. And so to start that out, we need to talk about the quantized electron wave functions and their energies. So you'll know the Pauli exclusion principle. So I was digging around last year. Instead of telling jokes, it was all on Zoom. And so I had all these memes, and I thought I would leave these in here because I just thought that was a great name, Wolfgang Pauli. And we'll talk about that Pauli exclusion principle today. So this is the potential energy term for a nucleus. We have the charge on the nucleus, that Z value. And then we have one of those charges, this elementary charge, that's what that E stands for, is positive for the number of protons you have, and then one of those is negative for the electron, and so that's why you have this negative sign out front. And then you have this distance from the nucleus to the electron, and so this is the potential energy term for every electron in the atom, and so you would have one of these terms for every electron in the atom. But for a hydrogenic atom, you just have one electron. So for a hydrogenic electronic structure, we just have one of these potential energy terms for the electron attracted to the nucleus. So Z would be 1 for that hydrogen atom. If we want to say a hydrogenic atom, you could say any atom on the periodic table as long as you just have one electron on it. So like uranium, or let's say mercury, you know, it has 80 protons. If we just had one electron on there, then you could calculate the potential energy for that one electron sitting very close to 80 protons. Then we have the Hamiltonian. You know, and all of this should look familiar when we did the Gaussian. The Hamiltonian was huge for all the electrons and the nuclei. But for just the single electron atom, this is the Hamiltonian. It has that kinetic energy piece. The T is kinetic energy, and the V is potential energy. And so the kinetic energy is that second derivative operator here. It has the mass, the reduced mass of the proton and the electron, and then the potential energy is that Coulombic attraction of the electron to the nucleus. So this reduced mass is essentially the mass of electron. That's pretty close for us. And so since the mass of the proton is 1,000 times heavier than the electron. And so then we have the Schrodinger equation. So it's operating on the wave function, and we have the kinetic energy piece, taking the second derivative of the wave function, and the potential energy piece multiplied by the wave function. It's an eigenvalue equation, and so we get the wave function back, plus these constants that come out, which are the energies. Now, in graduate school, I had to do this one by hand. We filled pretty much this whole board, something about that size, with all of the algebra and the calculus in solving this equation. One thing that helped us solve that equation was the separation of variables. So we have a three-dimensional space. Typically, we talk about x, y, and z coordinates in three-dimensional space, but for a spherical system, it makes sense to be in spherical polar coordinates. And so these have been transformed into the spherical polar coordinates, r, theta, and phi, for this system. So x, y, and z don't necessarily make sense in something that's spherical. And so we want to just talk about the distance from the nucleus and the angle. You can think of it as longitude and latitude. So we kind of have a spherical polar coordinate system for the Earth. Okay, altitude is r. So distance from the center of the Earth, or we call it distance from sea level. Okay, and then theta and phi would be longitude and latitude. So it's the same kind of thing in an atom. Okay, you have spherical polar coordinates, you have the angle around the atom and the angle down from the pole. And those tend to be separable. And so we can separate, in this case, altitude from the angles. And so we have this radial distribution function, which gives us our quantum number n. And if we look at the periodic table, coming down that left side, that period number, at least for those first two columns, that is the quantum number n. And so a lot of these quantum numbers you can see right on the periodic table. And so we will relate these to electron configurations and we'll relate them to the periodic table. So if I come in on rubidium with an electron in the s orbital on rubidium, which principal quantum number is it? It's n equals 5 for rubidium because it's on the 5th row. So that's a 5s electron. So if you understand how the periodic table is constructed, you can immediately see some of these quantum numbers. Okay. And then this L and M for the spherical harmonics come in, and those are the other two quantum numbers to describe the orbitals. And so those are our first three quantum numbers for atomic wave functions. Now this was a real mystery to the early folks in science, was they started to think about quantum mechanics as to how this electron cloud could be quantized. And that's what de Broglie did. When I talked about the history chapter, he said, well, maybe because the electrons are attracted to the nucleus and the wave function goes to 0 at infinity or infinite distance from the nucleus, maybe between this wave function going to 0 and the nucleus, it's like a violin string, because a violin string would have certain harmonics. And it couldn't have any tone. If you have a certain tension, a certain weight of string, and you pinch it at the ends, it's going to have a given tone or an octave above that tone or an octave and a fifth or 2 octaves. It's going to have quantized vibrations. And that was his idea in his thesis. Einstein read it and said, this has some merit to it, and he handed it off to Schrodinger, and Schrodinger is the one that solved the hydrogen atom problem. So Schrodinger was the first one to do this equation. That's why it's named after him. And these quantum numbers came out of that solution. So here's the energy equation. So let's, we've seen many energy equations, right? We have the essentially the particle in a box, E 1d PB. Does everybody understand what that is? 1d particle in a box. It's h squared n squared over 8ml squared. And we had the energy of rotation, which was B times J plus 1. And we had the energy of vibration, which was vibrational frequency times V plus 1/2. Now remember this B value, this rotational constant. I'm going to use our simplified version, was like 16.8, right? Over reduced mass, and distance. So just like our 1D particle in a box had mass in the denominator, our rotational wave function has mass in the denominator. And what is this vibrational frequency? Okay, let me finish my parenthesis there. The vibrational frequency was 1 over 2 pi c and the square root of the force constant over reduced mass. So mass is in the denominator. So in all of these other energy equations, mass was in the denominator. But here, this is interesting. We see mass here. Look at that. So that's my little sunglasses there. Look at that. But notice this. There's two things that have changed. Our energy equation is negative. So I'm going to put a big old exclamation point by that. So as mass goes up, energy still goes down. So in all cases, even in an electron system, if for whatever reason the mass of the electron would change, the energy would go down. Okay, it's not likely that that's going to happen, but the point is, it still behaves the way we expect after doing the particle in a 1D box. We have this intuition that if the mass of the system increases, the energy levels will get closer together and they'll decrease. Okay. What about quantum number? Over here, quantum number is in the numerator. And so as quantum number goes up, over here, the energy goes up. And here, rotation, here's J is the quantum number. As it goes up, energy is going to go up. And in vibrations, here's the quantum number. It's in the numerator here, essentially. There's no denominator. As it goes up, energy is going to go up. But here, the quantum number is in the denominator. But the energy is negative. So as the quantum number goes up in the denominator, my fraction gets smaller and smaller and smaller. It gets less negative. Okay, so it does go up. Yes.
What was it that you wrote about the U?
Those are little sunglasses. I'm just saying, look at that. Yeah, so it's kind of a strange symbol. And sometimes when I want to point out something if I'm taking notes or whatever, and I want to point that something's interesting, I'll put little sunglasses on it, or eyeglasses. Yeah. And so our principal quantum number, even though L is present in the potential energy portion of the Hamiltonian, we won't see it in a single electron atom, but we will see it in the multi-electron atoms. And so let's look again, to summarize, let's look at these energies. As mass goes up, energy goes down. So we expected to see that. As quantum number goes up, energy goes up. So notice when n equals 1, that's the smallest denominator that we can have, and energy is really low here. So here's our quantum number 1. Quantum number 2, we're dividing that by half. Okay, half squared. Okay, we're dividing it by 4. And then when it goes up to n equals 3, we're dividing by 9. Okay, and so you see as quantum number goes up, energy goes up, but the energy levels get closer and closer together as we go up in quantum number. What happens when these energy levels go like to zero distance? What have we done up here? We've pulled that electron off the atom. Okay, so this right here is the ionization limit. So as the quantum number goes to infinity, the energy goes to zero. Essentially, we have the electron and the nuclei separated at infinite distance. So that's the zero reference energy. As we bring the electron and the proton together, we drop in energy because opposite charges attract. And so we're giving off energy as we bring them together. So our atoms have negative energy. And this is exactly what we saw with Gaussian. All of those energies were negative because the reference point was the same as the hydrogen atom. We have infinite distance between all electrons and all nuclei. As we bring them together, energy is dropping and all the energies are negative. Okay, and as charge goes up, energy drops dramatically as well. So charge is in the numerator, and again, it's negative. So we have that 1s orbital. As we go up the periodic table, the energy drops dramatically. So let's talk about the radial wave function. It's an e to the minus r dependence. And if you just look at the wave function by itself, it looks like the electron is most probably, if we squared that, most probably located on the nucleus. Okay, and that's kind of a problem because there's an electron's negative, nucleus is positive. They would join together and annihilate each other. Essentially, the electron and the proton would merge and form a neutron. And so we'll get into that at the last part of this second course in April. Okay, so if you want to learn about nuclear chemistry and this crazy idea of an electron and a proton merging to produce a neutron, or a neutron spitting out an electron and becoming a proton, and atoms hopping their identities all across the periodic table, then I would encourage you to take the second course. Let me close the door for a second. And that's the other thing too, is there's a lot of folks that are in here in forensic chemistry, but it's just a couple of courses different between forensic chemistry and then the straight chemistry degree. And you have heard and know well that the forensic programs are really competitive and really hard to get into. Okay, there's, say, this many jobs for the forensic chemistry major, and you could expand it if you're willing to just go into straight analytical chemistry. But then if you broaden your degree to chemistry in general, the job market opens up considerably. Okay, so it's just something for you to chew on. Okay, because there's so many more jobs available, then the competition, according to other applicants and so on, drops dramatically. So something to consider. So why does the electron? How does the electron stay out of the nucleus? Well, remember we went to spherical polar coordinates. And so when you take into account, you integrate this wave function over all space to determine its probability of where that electron is, you have to include the r² volume element. So when you're creating the volume of integration, that volume goes to 0 at the nucleus. And so when you incorporate that volume element, then you have a most probable location for the electron. And that's right here at, at half an angstrom, so roughly 0.5 angstroms. This axis is plotted R over A naught. And so at 1, so R over A naught, that's 0.5 divided by 0.5. So this A naught is 0.5 angstroms. And that's the most probable location for the electron away from the hydrogen nucleus. But notice there's quite a wide uncertainty. The electron cloud is diffuse. I mean, that electron's smeared all over that area. But if you were to square it and you say, what's the most probable location? It would be right there at half an angstrom. Now, here's how the radial distribution functions change as you go up in quantum number. Notice that I was talking about that ball at target. This was, let's see, it was 71 miles across, so about 35 and a half. Okay, and that put us down in Spring, Texas. If that ball in front of Target in Huntsville was the proton and the hydrogen atom was where was the electron in the hydrogen atom? So, halfway, that southern part of the hydrogen electron cloud would have gotten us to Spring, Texas. And then the 3s electron for sodium, this was Argentina. So quite a big difference in terms of the radius of these atoms. One thing I would like for you to see, though, is notice the 1s orbital has 0 nodes. And look at the 2s orbital. These are the wave functions squared times the volume element. And so they're all positive here. But this is a node. It's called a radial node. The 3s has 2 of them. And so that you can expect that in all of these situations. The first the first time a particular type of orbital shows up, it has 0 nodes. And then as you go up in quantum number, it gets 1 radial node for every time you go up in quantum number. So the 1s orbital is the first time you have an s orbital. So the 2s orbital has 1 node. The 3s orbital has 2 nodes. The 4s orbital has 3 nodes, and so on. What about the 2p orbital? That's the first time you can have a p orbital, and we'll see why in a second. And so then the 3p orbital has 1 node, because that's the second time you can have a p orbital, or the second the next higher energy p orbital. And then the 4p orbital would have 2 nodes, and so on. The d orbital, this 3d orbital, that's the first time you can have a d orbital, and so it has 0 nodes. And so then the 4d orbital would have 1 node, and the 5d orbitals would have 2 nodes. And those are radial nodes. They're spherical. So they're not planar nodes or anything like that. And we'll see what these nodes look like in a minute. So here's the radial node for the it's like the 2s orbital. You see, so the electron's oscillating. You can think of this oscillation as it's expanding and contracting in all directions. And so this cloud is pulsing like this. Remember what these orbitals came from, the spherical harmonics. And so if you take a spherical shell, so instead of a sphere of metal, you've got a hollow sphere of metal. It's a shell. And so it's really flexible. And if you were to like play a really low bass tone on that sphere and it was hanging from a wire, you could hit that bottom oscillation where the whole thing is expanding and contracting in all directions. That's an s orbital. Okay. But if you get to a higher harmonic, maybe the side is denting in while the other side's bulging, and that would be a p orbital. We'll talk about these some more. This one here would be really what you get with a cloud. You have an internal part of that cloud that's expanding and outer part that's compressing. So let's show this. This is, let's say we draw this with the expansion arrows here. So it's expanding at some time, whereas this one is compressing at that same time. So this outer ring is getting more dense here, while this one gets less dense. And then sometime later, all these arrows switch direction, where this inside gets more dense and the outer ring starts to expand. And so those are radial nodes in an s orbital. So this is probably the most important slide on today's lecture. Okay. So this is review of all of the 4 quantum numbers in an atom. And so this absolutely goes back to freshman chemistry. So we have the principal quantum number. It does go up to infinity in theory, okay? So it's unlimited. And that designates what shell the electron is in, and those are the periods of the periodic table. So I already talked about n being that 1, 2, 3, 4, 5, 6, 7. We really only go up to 7. That's as far as we go. So even though it, in theory, goes up to infinity, at least in the ground state atoms, we go up to n equals 7. Then we have the angular momentum quantum number. This is the longitude and latitude quantum number. So how does that electron cloud change as it goes around the nucleus? This describes the shapes. And so these are numbers, but we use letters because otherwise everything would be a number and it'd be confusing as heck. So we've got the principal quantum number, which we keep as a number. That's the 1s or the 2p or the 3d. That 1, 2, and 3, those are n. The L is the letters. So we have S, P, D, F, etc. And notice this one has a maximum value. It cannot go above n. It can't even equal n. It can go to n minus 1, and that's it. Okay? So if we have n equals 1 as our principal quantum number, the only L we can have is 0. And that's why there's a 1s only. There's no 1p or 1d. Because L has a maximum of n minus 1. That shell's just not big enough to have a p orbital or a d orbital. But if we go to n equals 2, then L could be 1, because that's n minus 1. So we have an s orbital and a p orbital in the n equals 2 shell. This should make sense to you, okay? but it's always good to review. And then we have this M sub L, which is the magnetic quantum number. It describes the relative position of each orbital. And think of the p orbitals. They can be along the x direction, the y direction, or the z direction. And so that would be, again, these have a max and a min value. This minus L here is the min value, and L is the max value. And so this is a set that's bounded by L, and L is bounded by N. So they build on each other. So if I have p orbitals, L equals 1, and so I can have M sub L equal -1, 0, and 1 if I have a p orbital. Because I have the min value is minus L, the max value is plus L. So that's why I only have 3 p orbitals, not 4 or 5 or 6. So these 3 quantum numbers designate the orbital. And then we have the electrons, okay? We have the electron spin. So electrons have an intrinsic sort of magnetic moment. So they have, it's like a little magnet. And one way to get a magnetic field is for a charge to be spinning. So they called it spin. They, in my opinion, probably should have called it the magnetic quantum number, okay? It is called M for its magnetism, okay, but the little subscript S tells you this is the spin of the electron. So M sub S is plus or minus 1/2. And that's it, okay. So here's everything put together. And that Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers. So that means there's really a maximum of 2 electrons in each orbital. If we put a third in there, since there's only 2 flavors of electrons, spin up or spin down, they would have to match one of the ones that's already in there, and that has not been observed in nature. So that's where this exclusion principle came from. It's an observation. And so here's different examples of orbitals that you're familiar with. So it's based on this idea. We have the principal quantum number. We have a lowercase letter that describes the L quantum number. We have sometimes an M sub L, like this 4p0 over here. And then we can put a number as a superscript to indicate the number of electrons in that subshell. And so we can have a 2s1, which just says there's 1 electron in a 2s orbital. It doesn't make sense to put the M sub L on there because it can only be 0. So it's redundant to put a 0 on the lowercase s. Sometimes you'll see 4p0 because they're indicating that particular shell, but more frequently you'll see x, y, or z because we're just going to align those p orbitals up with the axes. And so let's look at the shapes of these orbitals. So here are the p orbitals, very familiar with these, but let's look at this conceptually. Yes?
So,
should I go back? Yeah.
well, you said that, and I've seen MO theory before, it's, X, Y, and Z. But
Yeah.
where, if we're using Cartesian coordinates, where do the polar coordinates come in?
Okay, that's great. A lot of times, since we're in the lab, we're using the sort of the lab frame. So in this case, the X, Y, and Z would be the lab frame. So we're saying as light's coming in our experiment and so on, it's coming in on the x-axis or the y-axis or the z-axis, and we can turn the atom mathematically or in our minds to line up with the X, Y, and Z of our instrument, okay? And you may say, but the atoms may not obey, right? But statistically, there will be plenty of atoms that do line up, and other atoms that line up with the y-axis on our x-axis and so on. And so when we do the selection rules, we're getting sort of the average behavior of the atoms. And so it all works out to where it's really these X, Y's, and Z's kind of align with what we have set up in our experiment. Whereas solving for these orbitals, we used R, theta, and phi in order to get the shapes. And so let me show you, this may explain a little bit of where these shapes come from, and it may explain also this R, theta, and phi. So if we look at the center of the atom, and we have this electron cloud around that atom, and so I'm going to go ahead and I'll try to match this, the y-axis here, the x-axis here, and we've got this electron cloud going around. Okay, so that's sort of the waist of the electron cloud. Does everybody see that? Now, if the top of this electron cloud and the way it's oscillating is expanding a lot on the top and a little bit less as you go down the side, to where it doesn't expand at all around the waist. And then on the bottom, if we draw the compression of that electron cloud, it's compressing a lot right here in the middle, but less as it gets closer to the waist. And then using our little r theta phi, if we take this r and we move it around and we map where is this expanding and where is this contracting, you see how it's oscillating up and down? That cloud's oscillating up in the picture I've drawn, and sometime later it'll oscillate down. Notice if I'm plotting out here, if I were to just plot the change, so I'm just going to plot this change right here, and I'm going to color that yellow, and I'm going to plot this change down here and color that green, and I plot it in all those directions. Notice there's no change as I come out here. And so if I use R to plot my change, then this R is going to be zero change. This is positive change. This is negative change. And the R that I'm plotting in this spherical polar system is the magnitude of the change, and then I use the color to describe whether it's positive or negative. I get this picture. So if we call that yellow positive and this green negative, that's the change in the electron cloud that we're plotting. So this is not a picture of the wave function, it's a picture of the change of the electron cloud. So I remember as a freshman and even later as in PChem, wondering how the electron got from one side of the atom to the other by going through the nucleus. When the nucleus is positive and the electron's negative, I thought that the electron was sort of orbiting in this dumbbell shape. It's not. The electron cloud is still spherical, and this is plotting how that cloud is changing. So the electron's still smeared over the whole atom, but it's changing in this particular z direction for that orbital. You see what we're plotting here? Okay. And so it's on both sides of the nucleus at once. In fact, it's this whole volume at once. And that volume is oscillating up and down on the z-axis. Okay. So that's what's going on with these shapes. And then the others are the exact same thing, only on the y direction or the z direction. Now, when we square that wave function, where the nodes are is essentially a zero probability, and where the lobes are, that's the maximum probability. And so we can say that because the kinetic energy is along the z-axis, that electron is spending most of its time on the z-axis. And the y, because that changes in the y direction, that's where the kinetic energy is. That means that electron is spending most of its time on the y-axis. So these are directional for the p orbitals. And that's why in Gaussian, when you add p orbitals to hydrogen, that really enables that hydrogen bonding to be modeled, because you're allowing directionality to those hydrogen 1s orbitals by adding some p character to it. And it allows phenomena like hydrogen bonding to take place. Is that legitimate for a hydrogen atom? Well, when a hydrogen atom is on a molecule, you bet. Because these orbitals are the hydrogenic orbitals that we're showing. So these orbitals only apply perfectly to a one electron atom. You start putting those atoms in a molecule, and now the electron can do a whole lot of things that it really couldn't do energetically if it was just one electron on an atom. Here are the d orbitals. And so these shapes, this is the dx times y orbital. And so if we were to look at that from the top, we would see that x times y pattern of plus, minus, plus, minus. And so we have the positive x values times the positive x values there. We have the negative y times the positive x. Back in the back, we have negative y times negative x, which becomes positive. And here we have positive y times negative x, which is negative. And so that's why that's the dx times y orbital. The same thing for the dx times z, or dxz orbital. So in that coordinate system, again, we have the positive, negative pattern. And we started seeing some of those kinds of patterns with bond stretches and so on, but this is where it really becomes obvious with these d orbitals. And here's the yz orbital down here. So that same pattern, plus, minus, plus, minus. Now this one's a little strange. It looks the same as those others, but it's called dx squared minus y squared. And remember when we were assigning Millikan symmetries, we said if you look in the positive x direction and it's the same sign as the negative x direction, that's x squared. Well, look here, x. If I look in the positive x, I have a positive. If I look in the negative x, I have a positive. So that's x squared. And because it's a different color than the y is minus y squared. So it's x squared minus y squared. So the y squareds are both the same sign, but because of that minus sign, they're out of phase with the x. And so this is squishing in on the y direction and squeezing out on the x direction, and sometime later it will reverse. And so this, in the d orbital, the electrons can go in two directions. They can go in positive and negative y and shrink in positive and negative x, or vice versa. And so this electron can interact with four things at once, whereas the p orbitals, it can really interact with two things at once. And then this dz squared is a little strange. It's actually dz squared minus x squared minus y squared. So let's see if we can understand that. You can see that it's z squared because on the z-axis I have positive and positive. So if I look in positive z, it's positive. If I look in negative z, it's positive. So that's z squared. The minus and minus means it's out of phase with the x and out of phase with the y. And the x squared is the same sign in positive and negative x. And the y squared is the same sign in positive and negative y. And so there's no node between those because they're the same sign. And so that's where that donut comes from. Okay. So do you see how that's a donut? It's x squared and y squared in the same sign. And so that has the same color, if you will, around that whole equator region. And so this is the z squeezing out on the z, while the x and y plane shrink, and then sometime later the x and y plane expands while the z axis shrinks. And so this thing can bond with stuff above and below and with things in the plane. Yes? Oh, it's, let me see. It's missing here. You see how it's missing in this one? And so it's used twice in this one. And so it's the linear combination. So every orbital is used the same amount of times. And so since it's missing from that particular one, see there's essentially this one is a 0 z squared plus x squared minus y squared. And since it was used 0 times here, it's used twice in this other one. So it comes from the linear combinations of atomic orbitals to make these, or linear combinations of these Cartesian motions of the orbitals. Does that help at all? Okay, that's all right. But it's not that important, to be honest. But it's just, that's why. Z is used twice in this orbital and 0 times in that one. Whereas X is used once in each and Y is used once in each. Okay. Now here's the shapes of the orbitals. We've looked at S and P and D, and here's F orbitals. So you see you get more nodes. You have some more more crazy stuff along this Z, the center one. Notice how if you, on these M sub L's, these are in order of M sub L. So when M sub L is -2, it's really really close, like all around the plane, the sort of equator. And when you're in the middle, when M sub L is equal to 0, you're looking at something that's along the vertical axis. And when M sub L is its maximum value, it's back to the equator. Same thing happens here for the F orbitals. So when the f orbital, the m sub l is 0, it's all along the z-axis. And then when it's at its minimum and maximum values, it's really around the equator. And then in between those, you have some combination of the others. Notice the s orbital is spherical. The p orbital is very directional. And non-spherical. And so you see dramatic differences between the angular momentum quantum number between S and P and D. You have very directional bonding for p orbitals and so on. But notice as you go up in angular momentum quantum number, it kind of becomes, when you combine all of these orbitals, spherical again. Because we have so many lobes and nodes that there's pretty much any angle this orbital can bond with. And so as you go up in angular momentum quantum number, it kind of approaches a sphere again, and it becomes less directional. So this angular momentum quantum number, it's this, if we think of this angular momentum, like the reason you can balance a bicycle very easily is because of the angular momentum of the wheels and them spinning. And the faster the wheel spins, the larger the angular momentum vector. And using a right-handed coordinate system, as the wheel is spinning like this with my right hand, it's spinning forward, the angular momentum vector is coming out the left side. Okay? So this angular momentum vector is quantized for atoms and for electrons and for rotational motion of all types down at the atomic level, which would be a really weird bicycle. So first of all, there would be a minimum energy, so the bike would never stop moving, and then it would jump, like it's quantized, and so you could pedal, and then you would instantly pedal extremely faster, and you would jump to another speed. You wouldn't have intermediate speeds, and so this spinning is quantized in the atomic areas, and so this angular momentum vector is quantized. But the thing is, unlike a bicycle system, we don't know where that L is pointed. So its length is quantized, but we don't necessarily know where in space it's pointed. And so that's why we have these cones here. So we don't know where L is pointed. It's somewhere along this cone, but we don't know where. So these right here are L. But if we were to put this in a magnetic field, then we could tell at least what angle it was pointed at. We wouldn't know around the z-axis where it was pointed in x or y, but we could tell sort of what its projection on z was. So that's what the m sub l is. The z component of the angular momentum vector is also quantized. So this m sub l is -2, 1, 0, 1, and 2 for an L equals 2 quantum number. And so that's where these m sub l's come from. It's m because if you put it in a magnetic field, then we can detect these energy differences. Otherwise, there's no energy difference. If you put it in an electric field, you could detect it too. That's called the Stark effect. And then if you have a little magnet in the system, like an electron, then they can interact, and that's called spin-orbit coupling. So because of these m sub l's can interact with magnetic fields, and the electron has a tiny little magnetic field, then you can have some coupling between the electron and the orbit that it's in. So an electron in a p orbital can interact with that angular momentum of the p orbital. And the electron in a d orbital, as it's oscillating around this thing, that little magnetic field can interact. And so what does that mean, interact? Well, it's spinning around. Think about the moon around the Earth. The moon, well, that's probably a bad example because the moon doesn't rotate. It's locked with us. But you could imagine if it was rotating, it could rotate with its orbit or against its orbit. And so that does kind of match with the electron. If it's oscillating around the the nucleus in a particular orbital with angular momentum, it can have a magnetic field that's with that magnetic quantum number or against that magnetic quantum number. And that gives you an energy difference. So these are fine splitting in the spectrum. We'll see some fine splitting. So let's back up to the hydrogenic energy levels. And here are the s orbitals, the like n equals 1. So 1, 2, 3, 4, 5. And this is S, P, D, F. Notice there's no energy difference based upon S, P, D, or F in one electron atoms. But there is an energy difference when we go to multiple electron atoms. So now we have 2s and 2p, 3s, 3p, 3d. And so when we put electrons in these atoms, you're going to have these electron configurations, like that one for oxygen, that has all of these electrons in these different orbitals, and you fill them in order. So practice your electron configurations, because this is what we're going to do next. And so if you want some review, let's say you sold back your freshman book, there's a link right here that I can post on Blackboard that will take you to a free Gen Chem textbook, and you can review electron configurations and you can practice on your own. So start that right away, start doing electron configurations and renew your knowledge of those things. Okay. And so that's the main point here. We can finish this out next time. All right.